everyone, and welcome to this live lecture. So I hope that everyone can hear me and see me all right. I'm trying to look at the chat during the lecture, so feel free to ask questions. And also I will be using this item pool website, so you can go to itempool.com/Kepler/live and ask submit your answers. There will be several of these quizzes. So the first one, just sort of a warm-up question asking what is your most favorite Platonic solid. It seems that we have a clear winner, but we won't know until I reveal the answers. So I will do that in a minute. Let me just quickly look at the chat. So VK asks, is this aimed at A-level students? And the answer is yes. So basically it's aimed at people at the end of their sort of high school years. I would say anyone aged 16 and above should be able to follow what I'm saying, and it is aimed to be an elementary derivation of the Kepler's laws. So we'll see how that goes. So let me perhaps finish this poll and reveal the answer. Well, there's no answer, there's no correct answer, but reveal what you have voted for. So most people seem to have liked the icosahedron the most. And in fact, I also voted, and I voted for icosahedron, so it's good to see that is people's favorite. But also dodecahedron got 3 votes, tetrahedron and octahedron got 2 votes each, and the set cube ended up last with only 1 vote. Well, at least the cube got 1 vote as well, so that's great. So as I said, this lecture is about the Kepler laws of planetary motion. And my aim is to show you how Newton's F = ma and the universal law of gravitation can be used to derive Kepler's laws. So that's the plan, at least. We'll see how it goes. So let me go to the first slide. So this is the story I wanted to begin with, and this is why I asked you about Platonic solids. So Johannes Kepler, the German astronomer, mathematician, had this idea at the end of the 16th century that well, at the time there were 6 planets known in the solar system, and he had this idea that maybe the 6 planets, the number 6, has to do with the fact that there are only 5 Platonic solids. And he had this idea that these solids, the planets should have their orbits as sort of spheres, and they would be spaced so that these Platonic solids nested within each other could give a structure to these spheres and a correct spacing so that the planets would keep their distance from one another according to these Platonic solids. So this is a great idea. This is a fantastic idea to have. And in fact, what Kepler imagined is that you take the orbit of Saturn, let's say, that's a sphere. That's what he imagined it to be, and you draw a cube inside of that sphere just so it fits in the sphere that is the orbit of Saturn. And within that cube, you would draw another sphere that fits just right into that cube, and that would give you the orbit of Jupiter. And then you would take the sphere of Jupiter, the orbit of Jupiter, you would draw a tetrahedron inside of it, just so it fits. So an inscribed tetrahedron, and within that you would draw another sphere, and that would give you the orbit of Mars, and so on with dodecahedron, icosahedron, and the octahedron at last. So this sort of idea, this structure, would give you ratios between the orbits of the planets, like so. So we see numbers like 1/√3, we see the golden ratio appearing. So it's all very exact and precise. The only problem is that it's wrong. So this is something that even Kepler realized, that if you fix the position of the sun, and let's say you fix the orbit, the distance of Saturn, and then you draw these distances given by the ratios that I just showed you, you will get the planets placed, the orbits of the planets placed like so, the distance from the sun, as in this bottom row, but the actual orbits and the actual planets are of a distances like so from the sun. So you can see that there are like big errors in this sort of in these distances. So it's inaccurate as a model of the solar system. So this is something that Kepler knew about, and he kind of discarded the idea, but even late in his life, he went back to it and sort of thought that it was he liked the idea so much so that even though he probably realized that it's not correct, he kind of was very fond of it. But my point is what I'm saying up in the top right corner is that just because your hypothesis is nice and you have a nice idea, it doesn't mean it has to be true. So beauty is not equal to truth. Okay, but of course then, because of this great mathematical achievement and idea with the Platonic solids, he got the chance to work with Tycho Brahe, the great astronomer who for something like 2 decades collected astronomical data. So basically astronomical observations without using a telescope. But so without using a telescope, he was able to collect astronomical data that were correct to 2 arc minutes. So 2 arc minutes is 1/30th of a degree. And if you know that how tiny a degree is, 1/30th of that is a great accuracy. So Tycho Brahe had the best data in the early 17th century, and Kepler inherited all this data, and from it he was able to come up with these 3 laws of planetary motion. So the first 2 laws he published in Astronomia Nova in 1609, and the third law he published in Harmonicas Mundi in 1619. So the first law, I'm sure you have all heard about these these laws of planetary motion, but let me just quickly go through them. So the first law tells you that the orbit of a planet is an ellipse. It's not a circle as ancient Greeks imagined and people up until Kepler imagined them to be. They always wanted to use circles and circles going along circles. So people were very keen on the idea that it has to be circles. Circles has to be used when you are drawing the planetary orbits. But in fact, Kepler, almost by accident, realized that the orbit of Mars is best modeled by an ellipse. So he was actually looking at Mars, but here on the image I have the Sun and Earth. Of course, it's not to scale at all, but the point is that the planet moves along an ellipse, which has two focus points, and in one of the focus points we have the Sun. Okay, so that's the first law. The second law is the area law, Kepler's second law, which says that if you connect the planet to the Sun, to the center, to that focus point, this line segment will sweep out these sectors, and let's say in each month it sweeps out one of these yellow sectors. And the point is of this law that in equal times it always sweeps out equal areas. Okay, so let's say in each month it sweeps out the same area, that line segment connecting the Sun and to the planet. Okay, and that tells you something about the speed of the planet, because in order, so since the ellipse is sort of an oval shape, it means that when it's further away from the Sun, the planet further away from the Sun, it has to move slower, because we have these long skinny leg of the sector. So this arc, the orbit, has to have a short arc on the far side of the Sun in order to have the same area. When it's close to the Sun, it has these tiny short legs, so it has to speed up and cover a lot of distance in the same time in order to have the same area for this sector. Okay, so that's the second law. And the third law is about the orbital period, is the time that it takes the planet to go around the Sun. So it says that the square of this orbital period is directly proportional to the semi-major axis of the ellipse, and that is the longest axis, the longest sort of the width of the ellipse. Okay, so it says that if you take the major axis or the semi-major axis and you take its cube divided by the orbital period squared, you will get a constant. And in fact, Kepler claimed that all of these ratios for any planets is always the same constant. Okay, so these are the three laws, and now with these laws we can start looking into the behavior of planets. Let me go back to item pool. So I ask you to go to item pool now and try and answer the next question. So which asks you about a year in Venus. So how long is a Venusian year compared to an Earth year is the question. Of course, we have three possibilities. A year on Venus could be longer than a year on Earth, or it could take the same amount of time. These orbital periods could be the same, or perhaps a year on Venus is less than a year on Earth. So it's a simple question. I have even given you a hint in the form of Kepler's third law and in the form of this image right here. So on this image you can see the Sun, and in front of the Sun, I don't know if you can see that small black sort of speck, that's Venus. So this is a photo taken from Earth, of course, about a Venus transit. So I'm curious to see if you understood Kepler's laws, you should be able to answer this one correctly. So as always, well, let me just put this in the chat. So you can go to itempool.com / Kepler / live and submit your answer on this website, and I will reveal what you have voted for in a minute or two. Okay, so I already see something like 15 submissions, which is good. My computer tells me that there are something like 42 of you, which is the greatest number of viewers ever. But so if you are watching and you haven't voted yet, go to itempool.com / Kepler / live, open it on a separate tab, and vote for your answer. I would be curious to see if it seems like most people voted for the same thing. So either all of these 15 people got it wrong, or it's good that we have a big majority of people getting it right. So there's a question by VK. What did I say about the orbital period? So the orbital period is the time it takes the planet to go around the sun. So that's basically how you would define a year on your planet, right? So a year on Earth is the time it takes for us to go around the sun once. Okay, so I'm going to, I think most of you who have wanted could vote, but don't worry if you didn't get to vote, there will be plenty of other opportunities. Let me just finish this poll and reveal the answers. The answer, so it was option C, of course. So a Venusian year is shorter than an Earth year. So, and this is something I actually can show you. So all you have to do is just take Kepler's third law and notice that if you want to get the same ratio of semi-major axis cubed over orbital period squared, all you have to notice is that Venus is closer to the Sun. So the semi-major axis, the numerator is going to be a smaller number for Venus. So in order to get the same fraction, you want the denominator, the orbital period, to be smaller, to be less as well, right? So that is all it took to answer this this question. But let me just do a short calculation for you. So here is a notepad in which I will be calculating the Venusian year for you. So we have the semi-major axis of Earth. I set it to 1 astronomical unit. So if you don't know what an astronomical unit is, it's just the distance of Earth from the Sun, sort of an average distance. It's something like 150 million kilometers. So let me set it to 1 astronomical units. For Venus, the same number is something like 0.7 astronomical units. For Earth, of course, 1 Earth year in Earth years is 1. Here is that same equation that appeared in Kepler's third law rearranged. So I did rearranged it to express the orbital period of Venus using the other three numbers. So in fact, since I'm working in astronomical units and Earth years, these two numbers, T Earth and A Earth, they are nothing but 1. So all we are doing is we are taking this number 0.7, raising it to the third power and taking its square root. So what we get is this number, 0.615, and this is in Earth years. So let me multiply that number by 365.25. So that's the number of days in a year on Earth, and here's the number that we get. So in fact, a year on Venus takes about 224 Earth days. Okay, so if you look this up, this is actually very close to the actual number of days it takes for Venus to go around. Number of Earth days it takes for Venus to go around the Sun. Okay, so all right, let me then move on from Kepler's laws. Now we have seen these 3 laws. We have understood them. Now I have to say that these are great. Kepler's laws were a great achievement of Kepler, but they are empirical, so they come from experience, from the measurements of Tycho Brahe, so they do not explain the cause of the motion of the planets. And in fact, for like a good 50 years in the 17th century, it was a great question. It was a challenge for the thinkers, the scientists of 17th century, to figure out questions like, what is it that keeps the planets on their orbits? What could be the source of this force? Well, here is an image of a 14th century illustration from a codex, in which you see these celestial spheres being rotated by angels who are turning handles. So people suspected that this is not the correct picture, the correct cause of motion. So they suspected that it has to do with the sun, but the correct form of this attraction by the sun wasn't clear until sort of the second half of the 17th century. And the way people like Newton derived this correct form of the gravitational force was actually using Kepler's laws. So here is Newton's great work, one of the greatest scientific publications of all time. It's Newton's Principia from 1687. So this was his great work, in which, among other things, he derived Kepler's laws of planetary motion using his second law, the law of dynamics, F equals ma, and the universal law of gravitation, that gravity weakens sort of with the square of the distance. It's inversely proportional to the square of the distance from the sun. Okay, so let me go over to my notepad and try to show you a derivation of Newton's gravity using Kepler's laws. Okay, so first we have to imagine that we have this circular orbit. So here is the center, here is a circular orbit, and we have to imagine a planet moving around in a circle. So what we have is, well, the circle has some radius, and the object moving along this circle has a certain speed. Okay, so that's the speed. This is the radius of the circle, and of course, at some later point, if it stays on the circle, it gets to some other point, and it will have sort of the same speed. Well, we'll see why is it that it will have the same speed. It has to do with Kepler's laws, but basically this is still the radius, this is the angle that changed. Let me call it delta theta, let's say. So what happened here is we had this object moving around the circle, and we have these velocity vectors drawn. So the point is that it moved from this point to that point on the circle. So it had changed its position by sort of delta r, okay? And its speed has also changed, well, in the sense that this vector, that was the velocity vector, got rotated. Okay, so this, well, this right here is delta v. And the main observation here is that this angle is the same angle that we had right there. It's delta theta. So if we now write down, so what I'm claiming is that these two triangles are similar. So since they have the same sort of, they are both an isosceles triangle with the same angle at the apex, what we have here is delta v over v. So the base of this triangle and one of the legs has the ratio which is the same as the same ratio of quantities in this triangle, so that's delta r over r. Okay, so if you have this, you can do the following. You can look at divide by the time it took for this motion to happen. So what you will get, and maybe multiply by v, what you will get is delta v over delta t is equal to v over r. So I multiplied by v, and I have delta r over delta t. So if this time interval gets shorter and shorter, this relation stays valid, and when delta t goes to sort of 0, what we are getting here on the left hand side is actually the acceleration, the centripetal acceleration of our body, of this body moving. And what we are getting on the right hand side is the speed squared over r, because delta r over delta t also tends to some quantity, and it's the rate, it's the distance over the time, so that tends to the speed. So that's why we have v times v over r when delta t gets shorter and shorter. Okay, so all we have here is we just derived the formula for the centripetal acceleration. So let me just write down Newton's F equals ma. So we are looking for the force acting on this object, keeping it on its circular orbit. So that's F equals ma, where a is the centripetal acceleration. So that we just noticed to be v squared over r. So we have m times v squared over r. Okay, now what is v exactly? Well, just think about this. So according to Kepler's second law now, so we will be using Kepler's laws. Right here we have to use Kepler's second law, because what it says is that in equal times it covers equal areas. This line segment sweeps out equal areas in equal times, and when we are talking about a circle, that means that the speed must be constant. Okay, so Kepler's second law, let me just write Kepler 2. So Kepler's second law says that v is constant, and it has to be equal to the circumference of the circle divided by the orbital period. So the circumference of the circle is 2 pi r, and it has to be divided by the orbital period. So why did I write this? So all I did was looked at Kepler's second law, so that the speed must be constant. So the speed is of course displacement over time, so this distance over time. So I took one full orbit, so that's that distance is the circumference of the circle, and the time it takes to do that one full orbit is capital T, is our orbital period. So this is the formula I got for v. Now I can square this and write the following. So if I square v, I get m times 4 pi squared times r squared over r times t squared. Okay, so this is what I got for the force. Now I can apply Kepler's third law. Okay, so Kepler's third law, which says that the distance cubed divided by the orbital period squared should give me the same constant. Let's call this constant capital K. And if I use that, I can write t squared as r cubed over k. So this t squared over there can be replaced by r cubed over k. So that gives me a multiple of k, well, a factor of k times m times 4 pi squared. Then I have r squared upstairs, and I have r times r cubed. Okay, so this is what I got by applying Kepler's third law. So if I simplify by r squared, you see that I got for f the following. I got that it's 4 pi squared k times m over r squared. So this is the inverse square law. This is Newton's gravity for the special case of a circular orbit. And you might be asking, where did I use Kepler's first law? So here I applied Kepler's second law, here I applied Kepler's third law. Where did I apply Kepler's first law? Well, I applied it in the sense that I took a special ellipse, that is the circle, for the orbit of my very special planet. Okay, so applying Kepler's laws can lead you to Newton's gravity, the inverse square law, in the very special case of circular orbits. And sort of Newton's great achievement and great idea was to take this form of inverse square law and apply it to not just circular orbits, but basically all planets and all objects which has mass. Okay, so this is why it's called the universal law of gravity. Now, let me go back to the slides now and show you, show you something that I wanted to say. So previously, that several people knew, of course, that this is the correct form of gravitation, of the gravitational force. So including Robert Hooke, people knew that it's probably an inverse square law, but the actual first proper mathematical treatment was given by Newton. Okay, so this is why it's his big achievement. Okay, so maybe it's time for me to tell you what's going to be included in this talk and what won't be included in this talk. So we've already seen Kepler's great idea. This is called the Mysterium Cosmographicum. It was a great idea, but alas, it was wrong. Then just now we've seen how Kepler's laws can be used to derive Newton's law of universal gravitation. Now the next task, and this is basically our main objective for this lecture, is to go the other way, use Newton's law of universal gravitation and derive Kepler's laws. So this is how science progresses. You take some things like Kepler's laws. These are empirical, observational laws. You deduce something from it, like Newton's law of gravity. You generalize it. You say that perhaps it applies not just to circular orbits, but to elliptical orbits as well. And then you prove that indeed this generalized in this generalized setting, the law of gravity still holds, because it gives rise to the Kepler ellipses, okay, and maybe much more. And in fact, that is the case. Okay, so this is the main purpose of this talk. We will see during this derivation that sort of the main idea, the main thing that we'll use is conserved physical quantities. So physical quantities that do not change in time. And you will see through this derivation how useful these conserved quantities can be. And then I'll finish off by discussing some of the effects of the Kepler's laws, the effects they had on other areas of science, and there will be a surprise at the end. So what is not going to be in this talk is differential equations. So usually what people do, so when you go to university, and let's say if you study physics, if you decide to go and study physics at university, you might see a derivation of Kepler's laws from the law of gravity. But that derivation, well, the way usually teachers present it is by solving something called the differential equation. And it involves some tricky substitutions, and it's not at all clear how you can think of such a derivation. And I think sometimes it might be even more complicated than it should be. So what I also won't have in this lecture is alternative derivations. So there are many ways to derive Kepler's laws. I'm only going to show you one way, but I will mention a few of these other ways of proving Kepler's laws. And of course, lots of historical details. So I'm not going to be able to tell you the whole story. It's a fascinating story. There are lots to learn, and I will give you some references, including this book by Arthur Koestler. So it's called The Sleepwalkers, and if you are looking for a good read about Kepler and Tycho Brahe, Galileo, it has it all. So it's a really good book written in a nice way about these scientists kind of sleepwalking into discovery sometimes. it's a really good read. I can recommend it. Okay, so let's see. Are there any questions? Yes. So at the moment, so BK asks. So the equation I derived is limited to circular orbits, and yes, that is the point. So at the moment, what we have seen is that the law of gravity is connected to circular orbits. It might be just to be restricted to that motion, but it will turn out that it in fact is not the case. Yes. Okay. So do ask questions if you have any. I'll try to answer them. Okay. So of course there is this word in the title, elementary, and I should explain what I mean by elementary. And I have found this this quote by Richard Feynman, who actually gave a similar lecture on the motion of the planets around the sun in the 60s, and he said that his derivation will be also elementary, but elementary does not mean it's easy to understand. Elementary means that very little is required to know ahead of time in order to understand it, except to have an infinite amount of intelligence. So this is typical Feynman half-jokingly saying that elementary means that each step is easy to understand. Well, each step is kind of easy to follow, and you are starting from something that is not that much. Okay, and in the end you will see this nice structure of your argument resulting in Kepler's laws in this case. Okay, hopefully. So what are we going to use for these things? Well, I will be using arithmetic operations, so addition, multiplication, division, so all of that stuff that people learn in primary school. Then I will be using basic geometry, so this is secondary school stuff, I would say, all to do with scalar products and vector products of vectors. So I'm assuming that you all know what the dot and cross products of vectors are and what properties they have, but I will be referring to these properties. So even if you don't know these properties, you just have to accept or believe what I say. But after the lecture, you can check that these things are indeed true. I'm not going to prove things related to these two operations, but I'm going to use them. So this is something that I would say is elementary at this point. And I will also be using a tiny bit of calculus. So I'm not going to solve differential equations and use that big machinery of analysis, but I'm going to use a tiny bit of calculus, which might be something that appears in further maths. I'm not sure, but it is definitely something that you would see in the first year of university, and that is how these products, the scalar and vector products, behave when you take the rate of change of these products. And there are these very simple rules that the way you take the way you differentiate, the way you take the rate of change of a scalar product is you take the rate of change of the first vector and the dot product of that with the second vector plus the first vector as the first vector's dot product with the second vector's rate of change, and the same goes for the vector product. So you take the first vector, take its rate of change, and then you rest for a bit, and then you take the second vector and its rate of change. Okay, so it's called the product rule, or sometimes it's referred to as the Leibniz rule. The way my teachers taught me at I think university is that you start differentiating, you get tired, so you don't do the whole thing. you just first differentiate the first factor, and then you add to that another term where you have differentiated the second factor after you rested for a bit, and it's the same for the vector product as well. So this is all I'm going to use basically. And if it seems easy for you, then mission accomplished. Then I proved my point. My point being that this derivation should be elementary. Okay. All right. Now let's see. So of course, over the years, as I mentioned, just quickly I want to go through this. So over the years, Kepler's laws have been derived in many ways. And a few examples are, of course, Newton, who was the first one to derive Kepler's laws. He used geometry and his calculus that he just developed to derive these laws from his universal law of gravity. Then there was Jakob Hermann and Johann Bernoulli in the early 18th century, who used polar coordinates and solved the differential equation. So this is actually the kind of derivation that people see at university usually. Then there was Laplace, the great French mathematician at the late 18th century. Had a different approach where he used these conserved quantities that I'm going to show you, but he also solved the differential equation. So after all, this was a bit more complicated than the thing I want to show you. And then there was a whole list of people doing the same kind of derivation in slightly different ways, but sort of the core idea for all of these people in the 90s and the 20th century, so Möbius, Hamilton, Maxwell, and Feynman, they all used this this notion of a hodograph, which is just the shape, the curve that is traced by the velocity vector. Okay, so we are not going to approach this in this way, but I just wanted to tell you about these different ways of deriving Kepler's laws. Okay, and for the last derivation is by two Dutch mathematicians, Van Handel and Heckman, from 2019, and this is the derivation that I'm going to follow, and I will give you a reference to this paper if you want to read Van Handel's and Heckman's paper. There will be a reference at the end of the slides. Okay, so this is the geometry plus conserved quantities type of derivation that I'm going to show you. Okay, so let me move on to the two-body problem. So because the sort of the Kepler laws talk about a planet orbiting the sun, I will start with the two-body problem, where we imagine the Earth and the sun gravitationally attracting each other, you know, with the same magnitude of force, but being, you know, pointing in opposite directions. So this is Newton's third law, of course. So imagine the two objects, the two point particles with masses m1 and m2 placed at positions of r1 and r2 in 3D space, and connect these two points, and let's introduce a new vector called r, which points from m2 to m1. So this is just the difference of these two vectors. It's pointing from the sun to the Earth at the moment. Okay, so this is r, and then we can express the force acting on m1 as minus capital G, that's the gravitational constant, times m1 times m2 over r squared. So r here is the distance between the Earth and the sun. So this is Newton's universal law of gravitation, Newton's law of universal gravitation. So we have the gravitational constant, the product of the masses, and dividing that is the distance squared. So the last thing we have here is this vector r connecting the two bodies divided by its own length. So if you see these letters without the arrows on top, those refer to the length of that vector. Okay, so r here denotes the length of my vector little r. Okay, so this is the distance between the 2 points, and here I'm dividing r by its own length, making it shorter by making it of unit length. So it's just normalizing the vector. So f here has this minus sign because, as I said, the vector r points from m1, m2 to m1, and f, as you can see here, this blue arrow, this force is pointing from Earth to Sun. That's the attraction of the Sun on Earth. Okay. Now the next thing I want to do is fix the origin in the center of mass. So what do I mean by that? So these two massive bodies have a center of mass, which is actually somewhere inside of the Sun, but let's just say it has to be somewhere along this line, okay, the center of mass. And what I'm assuming, or what I'm asking us to do, is to fix the origin of our coordinate system along that line in the center of mass. That basically means that if I take the center of mass, which is just m1 times r1 plus m2 times r2 divided by the total mass, that should be equal to the zero vector, sort of the origin of my coordinate system. So I didn't divide this by m1 plus m2 because I can just always multiply both sides by the sum of the masses. So this is just my choice, special choice of a coordinate system. So if I have this specially choose coordinate system, I can express these two vectors r1 and r2 using this vector little r. Okay, so my point is that I have this line segment connecting the two masses. I put my origin put the origin in the center of mass, so r1 and r2 can be expressed by using this vector r pointing from m2 to m1 and just basically correctly scaling them. Rescaling little r gives me r1 and r2, and you can see that in fact r1 pointing from the center of mass to the Earth should be a positive number times the vector r, and r2 from the center of mass to the Sun should be a negative multiple, some negative number multiplying little r. Okay, so you can use the first equation and the third equation to express r1 and r2 via this little r vector. And if you do that, in fact, you can express the total energy of this system of two masses gravitationally attracted to each other in a simpler way. So basically what I have here is the kinetic energy of m1 written as 1/2 times the mass times the velocity squared, plus the kinetic energy of the second body, the Sun, written as 1/2 times its mass times the velocity squared. And then I have the potential energy, basically the term that comes from the gravitational attraction. So this is minus capital G times m1 times m2 over distance divided by the distance. Okay, and the point is that since I was able to express r1 and r2 via this little r, I can express these velocities or these speeds using the speed of this vector coming from this vector little r. So let me just try to show you how I do that. So I'll switch to my notepad, and so what I'm showing you here is the previous formulas expressing R1 and R2 using the vector little r and sort of some combination of the masses, and that means that the speeds should also have the same relation. Okay, so this right here is actually v, sort of the speed of this vector r. Okay, so now we have these relations, and what I want us to compute is the kinetic energy. So it's 1/2 times m1 times v1 squared plus 1/2 times m2 times v2 squared. Now if I take these, well, and there is of course the gravitational potential minus capital G times the product of the masses divided by the distance between the two objects. So now I can substitute for v1 and v2 these expressions on the right hand side of each of these relations, and what I will get is 1/2 times m1 times m2 squared divided by m1 plus m2 squared v squared. Okay, so this is just v1 squared plus 1/2 times m2 times m1 squared, because I'm squaring the right hand side of this inequality, of this equality. So m1 squared plus m1 plus m2 squared times v squared, and then of course I have to subtract the gravitational, so that's G, gravitational potential. But the point here is now we have this combination of masses. So if I write 1/2 times m1 times m2 divided by m1 plus m2, okay, times v squared. So if I collect these common factors from these terms, so 1/2 is a common factor, m1 times m2 is a common factor, and also m1 plus m2 in the denominator is a common factor. What I'm left with in the first term, what remains is m2 divided by m1 plus m2, and in the second term what remains is m1 divided by m1 plus m2, right? So I hope that's clear. So I collected these common factors from the first two terms, and what I'm left with is this combination of the masses. But if you look at this carefully, these are two fractions with the common denominator. So it has m1 plus m2 in the denominator, and what it has in the numerator is also m1 plus m2. So this right here is equal to 1. Okay, of course I have to remind myself to include the gravitational potential, the potential energy, and so this is something I've been just carrying with me. So now I have the following expression for the total energy. It's 1/2 times m v squared minus k over r, where I introduced these two new quantities, m and k. M is equal to this thing right here, m1 times m2 divided by m1 plus m2, and k stands for this numerator, so that's G, gravitational constant, times the two masses. Okay, so this is what I end up with. So these are some newly introduced quantities. M right here So I can go back now to the slide. m1 times m2 over m1 plus m2 is something called the reduced mass, and this constant k is just proportional to the gravitational constant. So what you have seen here is that the total energy of these two bodies being attracted to each other gravitationally can be expressed as the kinetic energy and the sum of the kinetic energy and the potential energy of something that looks like a single object, right? So if you look at the kinetic energy term right here, it's just 1/2 times m times v squared. So it looks like the usual kinetic energy of expression for a single object. So the point is that you can replace effectively these two bodies by a single object having this mass of m1 times m2 over n1 plus m2. It's called the reduced mass, and with this sort of constant giving you the strength of this gravitational attraction. But in this rewriting of the two-body system as a one-body problem, now we have this one body with mass little m being attracted to the origin. Okay, so this might have been a bit, I'm not sure if it was completely clear. I hope it was. Let me move to item pool and ask something that might show us if you got this about the reduced mass. I have a question. Let's see if this works. So my computer is a bit slow. I just want to go to the next question. Here it is. So go to itempool.com/Kepler/live and answer this question. Okay, let me just put this in the chat. So the question is, first of all, I'm telling you that the sun is roughly 1,000 times more massive than Jupiter. Jupiter is the heaviest of the planets in the solar system, and yet it's only 1/1000th of the mass of the sun. My question is, what is the reduced mass of the Sun-Jupiter two-body system? So I even put here the reduced mass. So it's the mass of the Sun times the mass of the Jupiter divided by the mass of the Sun plus the mass of the Jupiter, and I want you to express this in terms of the mass of Jupiter. So all I want you to do is to go to itempool.com/Kepler/live and enter a number that you calculate by using this fact that the Sun is 1,000 Jupiter masses. Okay, so if you rewrite this reduced mass so that m Sun, the mass of the Sun, is replaced by 1,000 times the mass of Jupiter, you will get a single number in front of m Jupiter. Okay, so I hope this makes sense. Let me just look at the chat. So you can input it in any way you'd like. I believe if you tap on to or click on this input box, a virtual keyboard should come up where you can input mathematical expressions like fractions. But if you input decimal expressions to I don't know how many, probably a couple of decimal places, I think it should be accepted by the system. We'll see. But I think there should be the option of writing it as a fraction. Okay, in the meantime, let me just look at the chat. So yes, reality -3 says that m1 times m1 times r1 plus m1 times r2 equals 0. Looks like moments. Yes, I guess. And Luca M says, unfortunately, that procedure of reducing the number of bodies by 1 is not easy for more than 2 bodies. In fact, that is true. So this reduction of the 2-body system to 1-body motion it gets much more complicated when you have more than 2 bodies to begin with. Okay, so I already see 8 people have submitted their answer. I will give you another minute and then I'll reveal the correct number. Okay, so let's that probably gave enough time for everyone to. Okay, there's a new submission. So do let me know if you need any more time. So there's a question: how do you derive the gravitational force equation? You mean the form of the inverse square law? So I did that using Kepler's laws, but in the end you have to start from something, right? Right now what I'm claiming is that we try to go the opposite way. We, instead of starting from Kepler's laws and getting to the the law of universal gravitation, we are going the other way. We are assuming we have this law of gravity, and we are trying to get as much out of it as possible. If it works the other way around as well, if we can derive Kepler's laws in the end, that means that we replaced these 3 laws of planetary motion by just one single law of gravity. So we got a new, yes. So basically in this case now, the way we are progressing, it's just assumed. It is just something that we start with and see what we can get out of it. If we can get to the Kepler's laws, that means that we can just replace Kepler's laws by a simpler, a somewhat, well, definitely something that is only one thing instead of 3. So, and this is basically, well, this is I think a very nice example of scientific progress, because instead of having 3 things to keep in mind, Kepler's laws, you only have one thing, this form of the law of gravity, to keep in mind. So that's progress, I would say. And in fact, there are much more to be gained, obtained from Newton's gravity. Okay, so let me just close this poll. So the correct answer was 1000 over 1001. So yes, some people try to input something that's similar, probably not to enough decimal places, so that's fine. But the main point is here, that this reduced mass is really close to being one Jupiter mass. Okay, so if you have 2 objects, one of them is really heavy compared to the other one, like the Sun compared to Jupiter, the heaviest object, the heaviest planet and object in the solar system other than the Sun, you are getting something that is when you reduce the two-body problem to the one-body problem, the reduced mass that is in that one-body problem is almost the same as the mass of Jupiter. Okay, so that's my point with this quiz. Okay, so let's move on to now deriving the Kepler's laws. I will start with the second law, the area law, and I will show you a proof that is actually Newton's proof. So this is roughly how Newton proved Kepler's second law. So imagine you have the Earth in space, and from some external point we are looking at Earth, and we connect Earth to this external point. And imagine that we made the sun disappear. So we got rid of the sun, we got rid of all of the planets. It's only the planet Earth sort of sitting in space. Well, in fact, not necessarily just sitting, but the point is that the law of inertia tells us that if there's nothing acting on Earth, it should move in a straight line at a constant speed, which means that if we wait something like a month, let's say, our planet will move along a straight line, and this line segment connected to an external point will sweep out a nice triangle, right? So there is no sun, nothing acting on the planet, it's moving along a straight line with this segment sweeping out a nice triangle. Let's say we wait another month, so another month goes by and we have another triangle. And my claim is that these two triangles will have the same area. The reason they have the same area is that this side along which the planet traveled, these two sides are equal. So because it was equal times, and it was the planet was traveling at a constant speed, right? So it traveled some distance in the first month and then traveled the same distance in the second month. So these two triangles have the same side, have these sides being the same length, but the triangles are also of the same height, because if you look at the line of these sides, containing these sides, it's from a certain fixed distance away from this external point. Okay, so and that is the height. So this is a perpendicular line showing us that these two triangles have the same height. So they have the same base and the same height, meaning that the area, which is 1/2 times the base times the height, is the same for both triangles. Okay, so this was the case where we didn't have the sun, we didn't have anything else in place. Now let's assume that after 1 month we put the sun back into that point, external point that we have looked at previously, and we put it back in, turn the sun on just for a moment, okay, after a month. And that turning the sun on just for a moment gives the planet a tug, like a pull on the planet, which will result in sort of a motion of this planet being added to the previous one. So instead of going along the original red line, it's going to deviate, and in a sense that in a way that we are going to have a new orbit. But imagine that remember that we just put the sun back in for a moment. So after we switch off the sun, the planet still should still move in a straight line, in a way that this tug that the sun gave the planet should combine with the original motion, putting it up there, the planet. So what we got now is a third triangle, in fact, and my claim is that this third triangle has the same area as the second one. So it's easy to see that they share a common side. So we have this green arrow, this on the bottom. So that side along the green arrow is of the same length. It's the same side for both triangles, and they have the same height as well because they are between parallel lines. So the two green arrows give you two parallel lines, and these two triangles, the third triangle and the second one, are between these parallel lines, so they must have the same height. So again, the second and third triangle share a base, and they have the same height, so they have the same area. So what we have seen is that the first triangle had the same area as the second triangle, and the second triangle has the same area as the third triangle, so we can get rid of the second triangle, and this area law remains valid not only when we don't have the sun and the planets and anything, but even when we put the sun back in just for a moment, okay, after 1 month. So you can imagine keep doing this. So instead of these blue segments, so instead of going straight, the planet gets a small tug after each month when we just put the sun back in its place for a moment, and it forces the planet to go along this broken line, this red segment. But the point is that by the previous argument, each time this line segment connecting the planet to the sun sweeps out the same area, sweeps out triangles that have the same area, okay, each time. So this is after 4 months, but of course, so we get this orbit, and the area law, Kepler's second law, is valid at this point. But no one told us to choose to put the sun back in every month. We could do that every 2 weeks or every week, or if you look, but even if you don't look, the sun is there pulling on Earth constantly all the time. So if you would repeat this and further divide the time intervals, you would get a nice smooth orbit in a way that this line segment connecting the planet to the sun would sweep out equal areas in equal times. So this is the end of the proof. This is Newton's proof of Kepler's second law, the area law. I hope you liked it. When I first saw it, I thought it was really nice, using some elementary geometry to prove something about planets. I think it's fantastic to be able to do that. I mean, all we used is triangles, and we proved something about planets. Okay, so next I want to show you a bit more, well, the same thing, but a bit more rigorous maybe. So now we have the vector r, which connects our planet to the sun, sweeping out a triangle, right? So what we have here is the planet has this vector going to it from the center at time t, and then some delta t time later we have it in another position, but it sweeps out a nice triangle. And my point is that the area of this triangle can be calculated using the vector product. So now I'm starting using the vector product and scalar product. So if you remember what this vector product is it's a vector that you get from two given vectors, so that this new vector is going to be perpendicular to the previous two, and it will have a length that is that has the area of the parallelogram spanned by the two vectors that you start from. Okay, so the length of the vector product is equal to the area of a parallelogram spanned by the two vectors. So if you want to get the area of the triangle, you want to divide by 2. So that's what that is what is happening here. So we have these two vectors RT and RT plus delta t spanning a triangle, but if you would complete it to a parallelogram, you would get the length of the vector product. So I'm multiplying it by 1/2 to get the area of the triangle. Okay, so the rate of change in area is now given by this vector divided by the time that has passed, so the time interval. So if you divide this vector by delta t, what you see here appearing is delta r over delta t. And if you take delta t to 0, if you consider shorter and shorter time intervals, this displacement over time is going to tend to the velocity vector. Okay, so the rate of change in area is given by the magnitude of this vector, which is 1/2 times the position vector cross product cross multiplied with the velocity vector. Okay, and in fact we've seen that this is something that's constant, and this cross product of the position vector and velocity vector is very similar to something called the angular momentum. So if you have heard in physics, we have this physical quantity called the angular momentum, which is this vector capital L that is given by the position vector, the cross product of the position vector and the mass times the velocity vector. Okay, and what we have seen here is that it's a conserved vector. It's a fixed vector that remains the same as time passes. And in fact, what we have seen in the previous proof as well, Newton's proof, and what you can see here as well, is that the motion has to take place in a plane that is perpendicular to this fixed angular momentum vector. So we have this angular momentum, and since we obtain it from the position vector and the velocity vector and take their cross product, so L has to be perpendicular to the position vector and the velocity vector, and it's a fixed vector, meaning that R, the position vector, will be staying in that plane perpendicular to L. Okay, so it's a conserved quantity. The motion takes place in the plane perpendicular to L, and the area swept out in equal in 1 unit of time is of course the length of this vector. But if you look at this vector, you get this from L by dividing L. Dividing L by 2m will give you the rate of change in area. So the length of L divided by 2m is going to give you the area swept out in unit time intervals. Okay, so this is Kepler's second law, and in fact, if you looked carefully in Newton's proof, we didn't use anywhere the fact that the sun has the gravitational attraction that is inversely proportional to the square of the distance. So nothing was assumed about the strength of the gravitational pull. The only thing we assumed that the gravitational pull has a center, so it originates from one point. Okay, so in fact what you could prove, and here is a derivation, is that for any central force, any force that sort of originates from one point, this angular momentum is conserved, and Kepler's second law will hold for any central law, any central force law, not just the inverse square law. And let me just quickly show you how this can be proven. Well, there is that bottom line, but let me show you using my notepad. So here I have, just to show you this Leibniz rule that I showed you in the beginning, that I told you I'm going to use in action. So what we are trying to compute is the rate of change of the angular momentum. So that's capital L is written as r, the position vector, crossed with m times v. So we are trying to calculate the rate of change of this cross product. And remember, we have this Leibniz rule telling us how to do this. Well, we have to do it one by one. First, calculating the rate of change of the first factor, then leaving the second factor untouched, and then adding to that the rate of, well, the position vector crossed with the rate of change of m times v. Well, m is just a constant mass, it doesn't change. Okay, and this is what we are left with. Now let's look at what we have. We have r dot, the rate of change in position. Well, that's just the velocity vector, and we have its vector product with m times itself. Okay, and then what we have is the position vector crossed with m times the rate of change in the velocity vector, which is the acceleration, right? So what we have here, this first term has the vector product of a vector with itself, well, with a scalar multiple of itself. If you know about vector products, you know that this has to be the zero vector. Okay, so if you take a vector and take the vector product of that vector with a multiple of the vector, you get the zero vector. And what we have here is the position vector crossed with m times a, and that is the force, right? Newton's F equals ma is what we applied here. So what we have here is r cross F, and if F has the following form, if it's pointing in the origin, sort of the center with some magnitude. So this is the unit vector pointing towards pointing away from the origin, and this little fr would give us the strength, the magnitude of the force. Never mind, that is just a scalar, that is just a number multiplying this position vector. And again, you see something that we have seen just a moment ago, a vector product where we have basically a vector and its scalar multiple multiplied, giving us 0 again. So this is again the 0 vector. Okay, so what we started from is the rate of change of the angular momentum, and what we ended up with was the 0 vector. So what we see from this calculation is that the angular momentum is constant. Okay, so this is the conservation of angular momentum, and we did not assume that we have the inverse square law. We assumed a general central force, a general form for the force that was just pointing in the same direction towards the center, but we didn't say what the magnitude of this force was. Okay, now let's go to item pool again. So let me send you over to item pool once more, and let's try to answer the following question. So go to itempool.com /Kepler/live and answer this question, we have well, a rotating cloud of gas which shrinks to half its size. So imagine a cloud of gas which is rotating around some axis, and it shrinks to half its original size. The question is, how does its speed change? So what's going to happen to the speed of this rotating cloud? We have a few options. So the first option is that the speed doesn't change, it stays the same, constant. Or maybe the speed gets halved, so just like the size of the gas, it could be halved. Maybe the speed gets doubled, or the final possibility is that the speed gets quadrupled, that is four times as big. Okay, so I'm interested to see what you think. And I have a strong hint here in the form of an image, of a picture of a figure skater. So if you have ever seen figure skating, you should know what the answer is here, and it has to do. There's another hint. It has to do with the total angular momentum being conserved. Okay, so I'll give you another minute to think about this. What happens to the speed of this rotating cloud of gas as it shrinks to half its size? I'm interested to see what you think. Okay. So let me finish this poll and reveal the answer. I'm curious to see. So the correct answer was option C. Indeed, the speed gets doubled. Okay, so some people thought that it might get quadrupled, but in fact, if you want the angular momentum to stay conserved, remember the angular momentum was the vector product of r, the position, sort of the size of this cloud in this case, and its speed. So if the size shrinks to half its original magnitude, then the velocity has to double. Okay, so that's the idea. All right, so let's see, how are we doing now? Okay, now we can move on to the conservation of energy. Okay, so now we have seen that the angular momentum is conserved. Similarly, you can prove that in the case of our inverse square law, the total energy is also a quantity, a physical quantity that is conserved. Okay, so if you look at the total energy, it's 1/2 times m times v squared plus minus little k over r. Okay, here I have written a bit more general, written the energy in a bit more general form. So in fact, for any spherically symmetric force field, you will get your energy be conserved. And the way you can prove this is again a similar calculation. So here capital V is the potential energy, and the force is obtained from this potential energy by differentiating. So let me maybe quickly show you this derivation, but I guess I can already understand how it goes. Let me just make sure we really do. So what we have here is what we are trying to calculate here is the rate of change of the energy, right? So the energy is, of course, is written as 1/2 times m times v squared plus the potential energy, which depends only on the distance from the center. So that is why it's a spherically symmetric force field, because it only depends, the strength of the force only depends on your distance from the origin, and we want to calculate the rate of change of this quantity. Okay, so v squared, let me rewrite this slightly. So v squared, the length of the velocity vector squared, is the same thing as the velocity vector scalar multiplied by itself. So what I'm saying is that this is the scalar product of v with itself. So if you know your calculation with the dot products, you understand that taking the dot product of a vector with itself gives you the length squared. Now to this we add the potential energy, and we want to calculate the rate of change of this thing. So let's calculate the rate of change of the kinetic term. That is going to give us 1/2 times m times the rate of change of v dot v plus m times the v dot the rate of change of v. Okay, plus what we will get here is is the derivative of the potential energy, okay, multiplied by the unit position vector and the dot product of that with r dot. So this is something that's called the chain rule, what we applied here. The point is that what we are getting is, well, this is just the same two terms added up. So this is twice m times v dot times v multiplied by 1/2. So this is just m times v dot v. And then what we have here is this v prime, which is the force minus the force and the magnitude of the force times the unit vector pointing away from the center times well, dot product with r dot. Okay, so what we got here is nothing but m times v dot. So remember, v dot, the rate of change of the velocity vector is the acceleration vector. So m times a gives us f, the force, dot the velocity vector minus, well, what we have here is again the force vector times r dot, which is the velocity vector. So f dot v minus f dot v gives us 0 as a number, because we are taking the scalar product of f and v, right? So what we get here is 0, meaning that E, the energy, is constant. So the total energy of our system stays the same. Okay, so now we see that the conservation of energy holds true, In the Kepler problem, little f and capital V have these special forms. So the inverse square law and the gravitational potential that is inversely proportional to the distance. So what I want to show you next is another question in item pool. So let's head over to item pool. I'm curious to see if you can get this one right. So my next question is about objects that have zero total energy. Okay, so let's imagine that we have an asteroid heading in the direction, well, it kind of towards Earth, but it's going to miss Earth, so it's going to fly past Earth, but it has zero total energy. Okay, my question is, what is going to happen to this asteroid? Will it be pulled by Earth's gravity into orbit around the Earth? Will it perhaps escape the gravitational pull of Earth and go off into space? Or will it maybe fall back onto Earth? Okay, so I have these three options for you. Will it be put on orbit around Earth? Will it escape Earth? Or will it fall back into Earth, basically killing everyone in the process? Hopefully not. So let's see. Go to itempool.com/Kepler/live and vote for your answer. Okay, so I already see 2 people have submitted their answers. So again, we have this object with zero total energy. So the kinetic energy is equal to the potential energy. And my question is, what's going to happen to this asteroid, this object? Will it be put into orbit? Will it escape the gravitational pull and go off to infinity? Or will it perhaps fall back into the center of the gravitational pull, which in this case, in this very scary scenario, might threaten us on Earth? So what do you think? I'll give you another minute and then I'll close this poll. Okay, I don't see any new submissions. So let me just finish. There is one. Let me just finish and reveal the answer. I'm interested to see if people got it right. So the correct answer was yes, option B. It's going to escape the gravitational pull of Earth and it's not going to fall back on us, which is good. So if something has zero total energy, it means that it has just enough kinetic energy to overcome the sort of potential energy that is required to escape from the pool, okay, and go off to infinity. Now, let me go to my notebook and show you quickly how this can be used to calculate the escape velocity that is required to escape from Earth. Earth is gravity, right? So if you want to put something in, not just into orbit, but to send it into to the moon, let's say, what kind of velocity, escape velocity you will need, can be calculated. So let me just quickly go to my notepad and show you how we get this calculation right. So here I have the total energy, that is 1/2 times the mass of my object times its speed squared minus what was it, g times m1 m2 over r. Okay, so if this is 0, I can express v using the masses and r. Okay, so v squared is going to be in this case is going to be in this case 2g times m1 times m2 over m times r. Well, remember m was this reduced mass, but in the case of a light object compared to Earth, which has a little mass compared to Earth, this is basically going to be the mass of that object, and we can simplify by that. So this is roughly true, meaning that the escape velocity is going to be roughly equal to the square root of this expression, which is 2 times the gravitational constant times the mass of Earth divided by the distance from the center of the planet. So that's the radius of Earth. So now I can show you this notebook again and this calculation for the escape velocity. So here we have the gravitational constant g, and the mass of the Earth in kilograms, the radius of Earth in meters, and here I have this expression that I have just written in my notebook. So this is the square root of 2 times the gravitational constant times the mass of the Earth divided by the radius of the Earth, and this is what we get, 11,186.4 meters per second. So it is roughly 11 kilometers each second, so more than 6 miles per second that you have to go and speed your rockets up to in order to escape from Earth. Okay, so if you look at the escape velocity for objects from Earth, you will see a number that is very close to being this figure. All right, so now we can use this little detour into the zero energy possibility to say something about planets, right? Because a planet is staying on its orbit around the sun. So in order to have a planet gravitationally bound into an orbit around the sun, it has to have a negative total energy. Okay, the energy stays conserved, but in order for it not to escape from the sun, just like our asteroid did from Earth, we have to have its energy, total energy, be negative. So capital E is going to be less than 0. But of course, this total energy is 1/2 times the mass times the velocity squared minus k over r. So what we have here in the first term, the kinetic term in the total energy is always non-negative. It's either 0 or positive, and it's most likely to be positive. But even if it's 0, if we sort of omit this first kinetic term, and we are left with only the potential energy term, we will get something that is less than the total energy, right? We are omitting a non-negative number, so we are getting something that is less than or equal to the original expression. So what we can say is that this negative total energy is greater than minus k over r, and you can rearrange this inequality to see that r is going to be strictly less than minus k over e. And remember, e is a negative number, so this is a positive this is a positive quantity on the right hand side of this inequality. But what it tells us effectively is that r can never be larger than this fixed constant minus k over e, meaning that the planet will stay within a circle of radius minus k over e. So again, that's a positive number. Okay, so what we have seen here is that if we look at the sun in the origin and the planet moving around it, it will never escape from this circle of radius minus k over e. Okay, let's just connect the origin through the planet to a point on the circumference of the circle, on the perimeter of the circle, and this way we get a vector s. Let's also look at the speed, the velocity vector of our planet. That gives us a tangent line to the orbit of our planet. So this tangent line is called L. And what we can do with this point on the circumference of the circle, we can reflect it through the tangent line drawn to the orbit to get a new point. So this vector, I'm calling it little t. It's a vector that I got by reflecting this point on the circumference over through this line that is tangent to the orbit of my planet. Okay, and now a natural question to ask: what happens when the planet moves along its orbit? Well, of course, it's going to, let's say, go along the orbit this way, meaning that this point on the circumference is going to go around the circle. So you might think that when you reflect it over, reflect it through the tangent line, you might end up at a different place given by this vector t. But the point is that as the planet moves along its orbit, this tangent line will also rotate and sort of be more, well, horizontal in this case, leading to the reflection ending up in perhaps the same spot. So this is our geometric motivation to ask whether this point, this reflected point, will change in time or not. Okay, so this is our main question here. Does this reflected point change in time as the planet moves along its orbit? Okay, so let's try to express this vector little t using the quantities that we already know. Okay, so the total energy, the angular momentum, and things like that. So let's see if we can express this quantity. Well, if we want to go to this point given by the vector little t, what we have to do is go from the origin to r and all the way to s, and then we have to go down twice this distance because we are doing a reflection. We have the distance between the point s and the tangent line, and we have to go twice that distance in that direction to get to t, right? So what we are really doing is taking the vector little r, well, we take the vector s and subtract r from it, so to get this segment right here, and we want to basically project it over to this normal line, okay? Because that is parallel to this reflected line. Let me show you what I mean by that using my notepad. So here I have the same drawing, the same figure. So what we have here is this circle from which the planet can't escape, and then I want to have a vector that is perpendicular to the tangent line of the orbit, and such a vector could be the cross product of the momentum, linear momentum vector, that's just the mass times the velocity vector, and the angular momentum vector. Why? Because the linear momentum, the speed, the velocity vector times the mass points along the tangent line, so it's in this plane, and the angular momentum, remember, is perpendicular to the plane of the motion. So the angular momentum in this case is actually pointing right at you, perpendicular to your screen. So L is pointing right at you, and P is pointing along the tangent of the orbit. So if you take the vector product of these two vectors, you are going to end up with a vector that is again in the plane of the motion and pointing perpendicular to the tangent line. So that's our vector little n. Okay, let me write that down. So little n is P cross L. P again, let me just remind you, that's just the mass times the velocity vector. So that's the linear momentum, and L is the angular momentum of our body. And what we are trying to do here is we are trying to take this, find out what's the length of this segment. And for that, we are going to take this vector right here, which is S minus R, and we are going to project it down to this line, this perpendicular line. Okay, so let me go on to do that. So what I'm saying is, so let me just summarize what we know. We have this normal vector given by the vector product of the linear and the angular momentum, and then we have this vector pointing to the circumference of the circle, which has, the circle has radius minus k over e. Remember, e is negative, so this number right here is positive, multiplying the unit vector along r. Okay, so that's our vector s, and what we are trying to do is express this vector right here as a combination of the vectors that we already know. So what do we have to do? We have to take, in order to get t, we have to take the vector s, so go from the origin to all the way to this point along the circumference given by the vector s, and then go this way twice. So what is this vector from s to this tangent line? Well, this vector is s minus r. So this piece right here, s minus r, the dot product of s minus r with n, and appropriately sort of scaled. We have to divide n by its own length to make it a unit vector. Okay, so this is how you project a vector to a line. So this is the projection. We have to, of course, flip. So this is somewhere right there, some pointing in that direction. So we have to flip the sign and double its size. So this is how we get from the origin to t. Okay, so now we have this vector being expressed by using the things that we know. So let me go on and try to express this this projection of s minus r to n, the scalar product. So can we maybe obtain a nice form for this scalar product? Well, both s and r point in the same direction, so they are parallel vectors. They are both a multiple of r, and I can write this as minus 1 over e. I can pull that minus 1 over e out, and get E plus k over r times the vector r. Okay, so if you expand these parentheses, what you are going to get is minus 1 over e times k over r times r. So that's the vector s. And what you also get is minus 1 over e times r. So that's minus r. So that's just s minus r rewritten using the total energy. And n, remember, the dot product is taken with n, and n is nothing but this vector product of the linear and angular momenta. Okay, so this is the vector product of the linear and the angular momenta. That's the normal vector n. So now what we have here is a vector product of two vectors, and the position vector multiplied in a scalar product. Okay, so we have three vectors here. What we can do now, and it's a special property of the scalar and vector products, is that you can write the same thing, but the same sort of first term, and do the following. Take the first two vectors, take their vector product and the scalar product of that with the third vector. Okay, so you can basically change the two products. Okay, so this is something that these two products have in common. There is a nice geometric proof for this, but I'm not going to go into that. It has to do with sort of the geometric meaning of this triple product thing. So now what we have here is, you can recognize that right here what we have is the angular momentum. So that is capital L by definition, and it's getting multiplied to itself in this scalar product. So that will give us the length of L squared. Okay, so what we end up having here is minus 1 over e times e plus k over r times L squared. Okay, so this is what we got from the vector that we have to subtract twice of s after some rescaling. Okay, so let's see what that rescaling is. So that rescaling, that is n squared. Well, n squared is nothing but p squared times L squared. Okay, so we have this n given by the vector product of p and L. And since these vectors are perpendicular to one another, their vector product has a length that is the length of p times the length of L. So the length squared is the length of p squared times the length of L squared. But this can be slightly rewritten if we express p from the total energy. So for that, let me just quickly tell you that the total energy can also be written as p squared over 2m minus k over r. Okay, so that's the same thing. I have just rewritten the kinetic part using p instead of v, using the linear momentum instead of the velocity. Okay, if I do that, I can express p squared from this equation, and what I'm going to get is 2m times e plus k over r times L squared. Okay, so this is what I get for my normalization constant, this n squared that I have to divide by. So in the end, in summary, what we are getting here, if we put everything together, this vector t is going to be expressed as, you see, it's s minus twice this vector. Now we know what this vector is. We can put this all together and get 1 over E times M times the vector product of P and L, the linear and angular momenta, minus K times M over multiplied by R over its length. Okay, so this is what we get. Let me repeat that. So what we are getting here, so here is the same thing on the slides, what we have gone through. So in the end, we expressed this vector t using whatever we had before. So the energy, the linear and angular momenta, the reduced mass, and the position vector. So we expressed t by using these known things. Now, the next sort of question that naturally occurs is, of course, what we had before. Does t change in time? So that's the question. Does t change in time? Well, in order to answer that, we have to now take the time derivative, the rate of change of t. Okay, so let me do that. So now we are trying to calculate t dot. Well, remember that we had the following for t. We had 1 divided by E times M times P cross L minus Km times R over R, the vector R divided by its length. So we have to calculate the rate of change of this thing. Okay, now let's go and do the rate of change of P cross L, the vector product of the linear and angular momenta. Okay, so vector product and the rate of change of that. What do we get? Well, we apply the Leibniz rule. So first take the rate of change of P, cross that with L, and then add to that P crossed with the rate of change of L. Of course, the rate of change of L, we know that L is conserved, so this is just 0 right there. That's the 0 vector. So this second term is actually 0. What do we get for the first term? Well, remember, P was m times velocity, and we are looking at the rate of change of that crossed with the angular momentum. So that's m times the acceleration vector, so ma. So that's the force, right? So that's going to give us the gravitational force F crossed with the angular momentum L. Now, the gravitational force has the following form, of course: minus K times m divided by r cubed times r. So if you're wondering what this r cubed is doing here instead of r squared, well, we have to divide r by its length to get a unit vector, and then have minus k times m over r squared. So that is why we have 3 copies of r in the denominator, and we have to take the vector product of this force vector with the angular momentum, that is r cross p by definition. Okay, so now let's look at this triple vector product that is r cross p. There is a nice identity, a nice vector identity expressing triple vector products such as this in a nice and somewhat simpler form. You can do the following. You take the scalar product of r and v multiply with this number, you multiply r. So take the scalar product of r and p and multiply r by that number, and then subtract the scalar product of r and r and multiply p with that number. Okay. So did I? Oh, I made a small mistake over there. This right here should read v instead of p. Okay, and this vector here should read v as well. And there I got it right. So this vector should read v as well. So that's why I have this this m there. Okay, so what do we have now? Let's see. We have this triple product expressed as follows. So let me just rewrite this quickly. So r cross v is being expressed as this scalar product of r and r dot, basically multiplying the vector r minus the scalar product of r with itself, that's its length squared, multiplied by r dot again. Well, r dot. Yes, so you might be wondering why can I just say that the scalar product of r and v, that is r dot, as vectors gives me the product of their lengths. So for that, let me quickly say that if you take the scalar product of r with itself, which is its length squared, for this is true for any vectors, and I take the rate of change of this expression, then the equality still holds. And if you know to apply, well, here we can apply the Leibniz rule to get twice r dot, the dot product of r and r dot multiplied by 2, and on the right hand side we get twice r times r dot. So this is just something called the chain rule. First we have to differentiate r squared, the function r squared, that gives us 2r, and then we have to differentiate r itself. So if we get rid of the factors of 2, we get this nice equality of the dot product of the position and velocity vectors to be the product of the distance and the speed. Okay, so now we can use this triple vector product expressed as such to be used in our next calculation. Well, to continue the calculation as follows. So what we are doing now is putting everything together and finding that the vector product of P and L, the linear and angular momenta, will have a rate of change that is k times m times minus r dot over r squared times the vector r plus 1 over r times the vector r dot. Okay, so this was obtained by looking at this calculation right here of P cross L dot. We got to this point where we had to calculate this triple vector product that we calculated to and found to be this, and then we have to take the cross product. Then we have to just put everything together. Here we have a certain scalar constant, and we have to multiply that by this expression in this box, the right hand side of this box. If we do that, we'll get this expression, which is in fact nothing but km times r, the vector r, divided by its length, dotted, meaning that the rate of change of this vector. Okay, so the way you can see this, well, first you have to differentiate 1 over r to get minus 1 over r squared times r dot times the vector r, and then you have to differentiate the vector r itself, and this is how you get these two terms. Okay, so once you are at this point, you can just now go back to looking at your vector t, and you want to calculate its rate of change. Now let me see if I can show you this vector t. So we want to calculate the rate of change of this vector, but the first term was p cross l. Of course, E and M were constants, so we don't have to worry about that. But the rate of change of P cross L was exactly equal to, in the end, we found the rate of change of this other term in T. So let me just write that down. 1 over EM times P cross L minus KM multiplied by the vector r divided by its length and the rate of change of that. Okay, so this thing right here is the zero vector, because the rate of change of the first term is equal to the rate of change of the second term without the minus sign. Okay, so what we have found here is that this vector is zero. That is the rate of change of our vector t. Okay, so what we have proved here is that the rate of change of t is zero. T is a conserved quantity, this vector. So that point in the circle won't move as our planet goes along its orbit. So I hope that was possible to follow. It was a bit involved, probably the most the hardest calculation of this presentation. But now I can tell you that this vector little t is conserved. So that means, that will of course mean that, let me show you here, that will of course mean that the distance between t and r and the origin is going to be constant. So this is why we get here an ellipse. Let me first tell you about t minus r, the length of t minus r, plus the length of r itself, well, from the origin. The distance of r from the origin is the length of r. So what we get here, t minus r has the same length as s minus r, because the way we got t is by reflecting through this tangent line, right? Okay, so this is why t minus r is the same thing as in length as s minus r. Okay, and to this we add r minus the zero vector. If we look at the sum of these two distances, well, you can look and you can see that this is s minus r, and this right here is r minus the origin minus the zero vector. So this in fact here is just the length of s, which is the radius which was, if you remember, minus k over e, a constant, positive constant. Okay, so let me go back to the slides and show you that in fact what we have here is that what we have found finally is that the length, the distance of our planet from the origin and from this point T, if we take these two distances, r, the distance of r from T and the distance from r from the origin, we add these two distances up, we get a constant. We get a fixed number. And in fact, this is Kepler's first law. We have just obtained an ellipse finally. Now let me show you why is it really an ellipse. So if you look at this this notepad right here, we have two fixed points, 2 points that are fixed, and I have a piece of string which has a constant length, of course. Now I take my pen and stretch it out and start drawing so that the string is always taut. And what I'm getting here is an ellipse. So at each moment, what I have is, when I'm on the ellipse, I have these two distances from each of these points, the focus points, and when I add those two distances up, I always get the same number, which is just half the length of this string, right? So these two distances always sum to the same number. Okay, this is the definition of an ellipse, and this is how you can draw an ellipse using a piece of string and two pins. Now going back to my slides, I want us to now look at ellipses a bit and go to item pool once more. So let me go to the next question on item pool and see if you can answer this one. So the next question is about ellipses, and it says that we have a point P on the ellipse which has a semi-major axis A equals 3 and the semi-minor axis B equals 1. And the question is, what is the sum of distances of P from the two focus points F1 and F2? Okay, so again, A is that this the semi-major axis that is equal to 3 units, and B is the semi-minor axis that is equal to 1 unit of distance. And we are looking for the sum of distances of P from the two foci. Okay, so please go to itempool.com/Kepler/live and do submit your answer. I will also try to look at the comments. There's not much going on, which is fine. By the way, this of course this talk is going to be recorded and it's going to be put on YouTube, so you can always look back on it. And in fact, if you are watching this after the lecture on YouTube, you can go to item pool and you can take part in these quizzes. Now let's see. Okay, so are there any? Okay, there are 2 submissions already. That's great. Okay, someone has also submitted their answer. Okay, so let me finish this poll and look at the actual answer. So there are 2 competing ideas there, I think. So the correct answer is, of course, 6. So, but whoever has written 2a, that's also correct. So that's twice the semi-major axis. And in fact, if we look back at the notepad, so this distance, the sum of these 2 distances, is always the same. So if I go all the way to this point, okay, here I have so for the sum of these 2 distances, fp plus f2p, what I get here is I go from this focus point, f1, I go all the way to this side of the ellipse right there, and then there's this bit, the other distance is just this bit, which is the same as this one right there. You agree that this bit and this bit are equal? So what I'm getting here is I can just take this second distance and add it over to here, and in fact cover the entire major axis that is of 2a in length of the ellipse. Okay, so right now we actually have found the semi-major axis of our planet, because if we look back in this notepad, so what we have here is we have seen that this constant for the ellipse that we have just seen to be 2a is equal to minus k over e. So in fact, the semi-major axis of our ellipse is minus k over 2e. Okay, so we have one of the axes of our ellipse, elliptical orbit, and now let's look at the other one. So let's try to figure out what the other axis should be like. So for this, we have to calculate the length of t. So why do we need to calculate the length of t? Well, we know the length of a, the semi-major axis, and we know and we want to obtain the semi-minor axis. So in case we look at this configuration where this distance of 2a is given by these pieces of string as a plus a, then we have a right triangle right here with a hypotenuse a and 2 legs that are of a length b and t over 2. So t here is the length of our vector, little t. So you can see that we could use the Pythagorean theorem to obtain little b. Okay, so little b can be obtained if we know, if we would know the length of little t. So that is the next thing we are going to calculate in this. And then we are basically finished, well, almost finished. Let me show you the calculation for the length of t. So for the length of t, what we want to calculate is basically we could calculate the squared length of t. So if you remember, this vector little t had the following form. It was so the squared length of t is the same thing as the scalar product of t with itself, and little t had the form. Let me go back and show you that little t was written like so: 1 over em times p cross l minus k times m times the vector r divided by its length. So I have to take, if I want to find the length of t squared, I will have to multiply this vector by itself, which is 1 over e, well, we have 1 over e times m, so in both of these factors, so 1 over e squared times m squared. Then we have to take p cross l minus k times m times r over r and multiply it by itself. Okay, so here we have the length of p cross l squared. That's just p squared times l squared, since they are perpendicular to each other. Then we have the square, well, these two vectors multiplied. That will give, this is a unit vector, so that will give us plus k squared times m squared. Then we'll have these cross terms, so multiplying p cross l with r, with the term containing r, will give us minus 2. Two of these terms have the same form, so minus 2 times k m over r times the vector r, scalar multiplied by p cross l, basically. This is how we end up with this vector. And again, here we can do a bit of rearranging to get the following. Well, the first few terms don't change, and then we have minus 2 km over r times r dot, and now p cross l is again, remember, a triple vector product, because we have p cross l cross r cross p, basically. And this can be rewritten using the triple vector product formula that we have seen before, as p squared times the vector r minus r dot p times the vector p. Okay, so this is how it can be rewritten. So what we are left with here is 1 over e squared times m squared times p squared times l squared plus k squared times m squared minus 2km divided by r. And what we have here is, well, of course, here we will get r squared times p squared from the first term when we expand this bracket, these parentheses, and from the second one what we will get is 2, because of these two minus signs it's going to be a plus, 2k times m over r times the length of r squared times the length of p squared times the cosine of the angle between these two vectors r and p squared. Okay, so this is just the scalar product written out in this usual geometric, using its usual geometric definition. But what you can notice here is we have 2k m over r times r squared times p squared, and that again multiplied by the cosine of alpha squared. So we can use the nice trigonometric identity that is the cosine of squared plus the sine of squared of an angle is equal to 1. So we can use that to get the following: 1 over e squared times m squared multiplying p squared times l squared plus k squared times m squared minus 2km over r times r squared times p squared, and here we have minus 1 plus a cosine of squared giving us minus a sine of squared, sine of alpha squared. Okay, so here what you can notice that this expression right here is the length of the vector product of r and p squared, and the vector product of r and p is the angular momentum, so that is the length of L squared right there. So what we get is 1 minus e squared times m squared times p squared times L squared plus k squared times m squared minus 2km divided by L times L squared. Okay, so this is what we got. Let's see if we can pull these things together. So here we have a fraction with, of course, e squared plus m squared in the denominator, and upstairs what we have here is, notice that we have L squared multiplied by p squared and multiplied by minus k over r times 2m. Okay, so it is exactly the energy multiplied by 2m what we have as the factors multiplying L squared. So this is 2m times e multiplying L squared in the brackets plus k squared plus times m squared. So this is the length of our vector t squared. Okay, so this is the length that we were looking for. So, and now we can go on to finding the semi-minor axis of our ellipse. So here's the same derivation. Feel free to pause the video if you are rewatching this and just go through it yourself. But I'm going to the next slide where we apply Pythagoras's theorem, as I explained it before, to find the semi-minor axis. So here we have the right triangle with the hypotenuse A and the legs B and T over 2, and we are looking for B, so B squared should be equal to A squared minus T half T over 2 squared. If you plug in what we have just found for the length of T, you will get that B squared is equal to L squared over minus 2em. Okay, so the two axes of the ellipse are A, which is equal to k over minus 2e, and B, which is equal to L over the square root of minus 2em. And remember, e is a negative number, so what we have under the square root is a positive expression, is a positive number. So now we have the axes of the ellipse, which means that we can in fact prove and derive Kepler's last and third law using the fact that what we have seen before is that the position vector r sweeps out an area of L over 2m each unit of time, so each second, let's say. But it also sweeps out the full ellipse during the orbital period. So it means that the area that is swept out on the one hand is L over 2m times the orbital period t, but in the same time it sweeps out the area of the full ellipse, which can be written as pi times the product of the semi-major and semi-minor axes. So pi times AB. So from this you can express t as 2m times pi times a times b divided by L, and take the square of t in that expression. So if you do that, you get 2 pi squared times m squared times a squared times b squared divided by L squared. And now you can simply plug in the expressions that we got for a and b and square those. If you do that in the numerator, and you will notice that lots of things cancel, and what you are left with is 4 pi squared times m over k multiplied by the semi-major axis cubed. And this is exactly Kepler's third law, because if now you rearrange this equality, what you get is a cubed over t squared equals k over 4 pi squared times the reciprocal of this reduced mass. Now, if you substitute everything back into this expression, so little k, we introduce little k to stand for capital G times m1 times m2. So capital G is of course the gravitational constant. M1 and M2 are the two masses that were involved in the two-body problem. And the reciprocal of the reduced mass is of course just the sum of M1 and M2 divided by the product of M1 and M2. And you can notice that the product of M1 and M2 cancels. So what we are left with is G over 4 pi squared times the sum of the masses. And if M1 is the mass of a planet and M2 is the mass of the sun, then what we have is M2 being much greater than M1. So if we add that tiny bit of M1, mass of M1 to this great mass of the sun, it's almost as if we didn't do anything. So roughly what we got for a cubed over t squared is roughly G, capital G, the gravitational constant, times the mass of the sun over 4 pi squared. And this is a constant. This would be a constant for all planets, of course. But you can see that the exact formula, so Kepler's third law, is just an approximation in the case when the sun is much more massive than its planets, which is to a good approximation is the case. So this is now Kepler's third law that we have now. And I can show you one more thing in this notebook. I prepared something that is the geosynchronous orbit, the size of the geosynchronous orbit that you need. So what you want to have is a satellite sent into orbit which goes around the Earth, and if you look up to the sky, you would see that satellite always in the same spot in the sky, because it would rotate, go around the Earth just as the Earth rotates around its axis. So it should have an orbital period of, that satellite should have an orbital period of a day. So given in seconds, it's 60 times 60 times 24. And from Kepler's third law, in which now we know what this exact constant is. It was g times the mass of the Earth over 4 pi squared. That constant multiplied by t squared and taken the cube root gives us the semi-major axis for the orbit of our satellite. And let's see what that is. Well, of course, the number of seconds in a day is 86,400, and the size of the geosynchronous orbit is 4.22 times 10 to the 7th meters. So that is something like 42,000 kilometers, if I'm not wrong. So if you look this up, the radius of the geosynchronous orbit, you will find a number that is pretty close to this number that we just got. Okay, so going back to the slides, all I have to say now is just summarizing, telling you what the moral of this story was. So you notice that this vector t played a very important, a crucial role in our derivation, and in fact this vector t is proportional to a very famous conserved quantity in physics, which is called denoted by capital A, and it's called the Laplace-Runge-Lenz vector. It is the worst name for such an important quantity ever, because Laplace-Runge-Lenz doesn't tell you anything about what this vector is, but it is basically an axis vector. That is why it has this letter capital A to denote it. So these the moral of the story that conservation laws are basically very, very important and very useful. We have seen that the conservation of angular momentum led us to Kepler's second law, and the conservations of energy and the vector t led us to Kepler's first law and Kepler's third law. Okay, so this is how we used conserved physical quantities that do not change in time, to derive Kepler's 3 laws of planetary motion. Okay, so of course we could count up how many conserved quantities we found, and in fact we have this angular momentum, which is a 3-dimensional vector, so it has 3 components. Then we have the vector t, which also has 3 components, so that's already 6 numbers. And then we have the energy, which is a single number as a scalar quantity, so that's a 7th component. So we have 7 things that are conserved, but in fact only 5 of them are independent, because the vector t and so the vector a is in the plane of motion, so it's perpendicular to the angular momentum. Remember, the angular momentum was perpendicular to the plane of motion, so their scalar product has to be 0 always, and also the energy can be expressed using this Laplace-Runge-Lenz vector and the angular momentum in this way. So E can be expressed using the other 2 conserved quantities, and there is a relation between the components of A and L. So in reality we only have 5 independent conserved quantities, which is another way, well, which could also mean, what is actually true is that this Kepler problem of planetary motion is a superintegrable system. So this is just something I wanted to mention because my research is on integrable systems. And integrable systems is an area of mathematical physics where you have many of these conserved quantities, and you can use them to actually solve the equations of motion, just like we did here, and prove very useful results about your physical system that you are interested in. Okay, so as epilogue, I would say that the effect of Kepler's laws are too many to count. Of course, it gave us an accurate model of the solar system, but not quite accurate. So that's the perihelion motion of Mercury I'm referring to. So it was so accurate that indeed it took a good number of years to notice that Newton's law of universal gravitation cannot describe the motion of the planets very well to a high accuracy. So there was the motion of the Mercury. So the closest point on Mercury's orbit, when it gets closest to the Sun, is called the perihelion, and that elliptical orbit of Mercury is rotating slowly due to the effect of the other planets, the gravitational effect of the other planets. And there was a slight deviation in this perihelion motion of the Mercury. Newtonian gravity couldn't account for something like 38 arc seconds in that motion. So the way this ellipse was turning was not described accurately by Newtonian gravity, and that was only put right by Einstein's general relativity. So that is a nice sort of nice way of tying it in with general relativity. So it was accurate all the way to the innermost planet, and sort of the largest gravitational effect the Sun has on a planet. Newtonian gravity was accurate all the way to that point, but then it had to be amended by Einstein's relativity. Another effect of the Kepler's laws, I would say, is in the early 20th century, Rutherford had this scattering experiment in which he bombarded a golden plate, atoms in a golden plate with electrons, and they thought that these electrons would scatter in all directions, sort of not distinguishing any direction in particular. And in fact, what they have found is that most of these electrons went straight through the atom, the plate that they bombarded with. So most of the electrons ended up on the other side of this plate, but some of them were deflected like extremely, which they explained by a new model of the of the atom, in which in the very center of the atom we have a positively charged core, which not gravitationally but in a Coulomb force sort of attracts the electron and deflects it when you hit it just the right way. The atom deflects this electron via its nucleus. So that led to the discovery to the atomic nucleus. Then there was, of course, Pauli in the early days of quantum mechanics, before even Schrödinger writing down his equation. Pauli was able to use the quantum mechanical version of these objects that we just used. So something like the Runge-Lenz vector can be understood in terms of quantum mechanics. And Pauli in 1926 was able to calculate the energy levels of the hydrogen atom. So basically using stuff that we did in a quantum mechanical setting. And that was before the Schrödinger equation. And finally, the reason, so we could of course always ask what's the reason behind all of these conservation laws being there in the Kepler problem. So why is the energy, the angular momentum, this Runge-Lenz vector, why are they all conserved? And it has to do with the hidden symmetries of the Kepler problem. So this is something that happened in much of 20th century physics, where people tried to connect conservation laws to symmetries using what's called Noether's theorem. So Emmy Noether, the German physicist and mathematician, theoretical physicist and mathematician, had this nice theorem connecting symmetries to conservation laws, and the fact that the Kepler problem has this many conservation laws hints at the fact that there are lots of hidden symmetries, and the study of symmetries in mathematics is called group theory. And this way, through the Kepler problem and the hydrogen atom, physicists started to use group theory in their work, and much of particle physics relies on these group theoretic ideas of mathematics. Okay, finally, just to finish off, I would like to go to item pool one more time and ask you how many planets are there in the solar system. Okay, so this is just for fun. Please go to itempool.com/math/Kepler/live and answer, well, input your answer. How many planets are there in the solar system? So I would be interested to see what you think. There is of course only one correct answer when it comes to the number of known planets. There are already two answers, which is kind of fun because it means that people don't agree on the number of planets. So I'm curious to see as to what we end up with. Okay, so let me finish the poll and reveal the answer. Hopefully no one gets offended by the answer. So it's 8 planets. There are 8 planets in the solar system. So if I just go, but someone has written 7. Some people one person has written submitted 1, and that is 9. Sorry. So that person who has said it's 9 probably thought of this guy, or rather this guy. So this is of course Pluto, as was nicely captured by the New Horizons spacecraft a few years back, so there are 8 planets. Pluto has been demoted to be a dwarf planet in a good number of years ago now. So this is a cartoon version of Pluto meeting New Horizons and being very happy that it's going to it's getting a visitor, but that was a very short visit, so the cartoon is a reflection of that. Now let me before I finish, let me just say that the study of planets in the solar system is still a very active and ongoing research, and there are even ideas about a 9th planet far out in the solar system, basically outside of the Kuiper belt. There is an idea about a hypothesis about a 9th planet which would explain some of these highly elliptical orbits of objects, as I said, far outside of the Kuiper belt. And that idea actually is partially due to Mike Brown's work, who is known as Pluto Killer on Twitter. He was actually the person who was in this committee demoting Pluto to a dwarf planet from a planet, and rightly so, if I may add. This is an ongoing research. Of course, they have not found Planet 9 just yet. So let me just finish the lecture by saying that I hope that this lecture showed you how theory and experiments work together in physics. So there were observational facts and there were theoretical derivations, and by the words of Einstein, I would say, which he wrote for the occasion of the 300th anniversary of Kepler's death, it seems that the human mind has first to construct forms independently before we can find them in things. Kepler's marvelous achievement is a particularly fine example of the truth that knowledge cannot spring from experience alone, but only from the comparison of the inventions of the intellect with observed fact. So Einstein is basically saying that the ancient Greeks were studying conic sections and ellipses only for Kepler, a couple of millennia after that, to discover them in the orbits of planets. So I would like to thank you for your attention. If you followed all the way through, you deserve some sort of a prize. And if you watch this lecture on YouTube, well, after it was live streamed, thank you for your attention as well. I hope you enjoyed the lecture. I would like to ask you people to complete a feedback form, so I see what things you liked, what things you didn't. I know it was really long, this lecture, so never mind the length. Just try to give me some sort of a feedback, whether you like this format or not. I would be interested in hearing from you. So that is all I had to say. Thank you very much for your attention, and I'll see you next time.